In this tutorial, we're going to be having a look at the net moment caused by the coats and the net moment caused by each of the components of the stand. And we're going to come up with a figure of the factor of safety for overturning for this. So just a measure of how safe this is, how easily overturned it is. And we're going to work out whether or not this actually does fall over or not, given the most unstable condition. We're going to add in an accidental destabilizing load as well. For example, someone could knock the stand quite reasonably from the side, and that's something that we need to take consideration of. So those three things we're going to add in to our stability results, and they're going to feed our heads-up display, and they're going to feed our multi-objective solver and our single objective solver in the next tutorial. Right, so first thing we need to do is grab a null item component. I'll explain why we're doing that in a second. So null item. And then we're going to list item, retrieving a specific item from a list. And I just want to take whatever comes out of here, I want to have the first item. And I'm going to feed that into a gate. Stream filter, which is a gate again, terminology. Right, and I want to set the value of true as 0. Now, what I'm doing here is, I'm going to group those. What I'm doing here is I am accounting for the fact that if the base is a certain size, if it's very small, then all of the coats will produce a destabilizing moment, and none of them will provide a stabilizing moment. And let's turn on some of the coats to see that in action. Where did we get to? Least balanced. Here we go. So let's add in some geometry, the geometry bin. So there we are. So if I were to make the base of the stand very small, we can understand that all of these are contributing to destabilizing. Whereas if I make the diameter very big, then some of them actually aren't. And potentially if you decide to make the diameter boundary even bigger, they might all contribute to the stability of the base. And we want to be able to know whether or not that's happening. If we don't get any data feeding through into our results, we will get a null flag, and that can disrupt the flow of our script. So I'm going to connect up list A, remembering that either of these could be null, could have nulls in them, and we want to know that. And if there are no nulls, then we want the data to flow. So if it's false, if there are no nulls, we want that data to flow through. What is that data? The distances, the lever arm of the coats. But if there are nulls, so if all of these are null, then we don't want anything to follow through. The reason for that is because we're going to be multiplying by a load. We don't want any of the nulls to multiply by a load. So let's copy that. Control C, Control V. Oh, that was lovely and slow, wasn't it? And we're going to, instead of plugging that into list A, it'll be list B for both of those. Nice and simple. And then we're going to use mass addition. For both of these. Yep. So these are lever arms on the right and on the left of our axis. Let's add in a panel here of 50. You might choose a higher value, but I'm going to name that weight of single coat in newtons. It's about 5 kilograms. You may think that we should have a larger value there. Well, that's debatable. So choose whatever you wish. And I'm going to multiply both of these by the coat weight. So we should get moments here. And I'm going to choose addition, feed in this top one into A, and I'm going to add another one in just a bit lower to feed the lower moments. Let's label them just for clarity. So this one is the stabilizing moment in Newton meters, and this is the destabilizing moment in Newton meters. And then this whole group is performing another function, isn't it? It's calculating the net moment created about tipping plane. That's all that's doing there. So we have destabilizing net moment from the coats and stabilizing net moment from the coats. And where the net destabilizing moment from the coats is null, because none of them are, they're all on the left of our tipping plane. At the moment it's not, but they could be. When null is fed through there, we'll get a 0 distance. That 0 distance will be multiplied by 50 and remain as 0, so we won't get any false moment there. And then this we will call add a panel, so we can see what's going through, and we'll call that the sum of the destabilizing moments, to be added to in a second. Okay, and this one, that is a sum of the stabilizing. Whoops. There should be some of destabilizing. Moments. Right, so there we've got our two. I'll move these down a little bit lower because we're going to include other values in here. The sum of destabilizing moments, we're going to have another entry. So if you zoom in on the component and press insert parameter, that allows us to add as many as we like. You can add hundreds if you want, probably. I've not gone that far. Let's add in our accidental destabilizing load here. So add a panel, type in -50, add another panel in, and type 1.5. So the -50, as you probably guessed, is the accidental horizontal action. In newtons. Let's expand it so we can actually see the text. Great. And this one is, have you guessed it, the height of the action from base in meters. So all we have to do is multiply this together and we get our moment. So let's name that accidental destabilizing load. In newtons. Great. So we can add to the sum of destabilizing moments, we can now add our accidental load. And let's add in a panel to that too, so that we've got an idea of what the figures are doing. We can see that the destabilizing moments are negative and the stabilizing moments are positive. That's really helpful, isn't it? Right, we're running out of space here on the canvas, so I'm going to move that up actually slightly out of the way. Now we need to calculate the net moment of the components, and we're very much in the same setup as with the coat. So let's just copy this here, move it down, We actually don't need the mass addition. Yeah, we don't need to multiply everything. Let's take the name and say Coats. No, this isn't Coats, is it? Yeah, just ignore what I'm saying. Right, add in a multiply component. Copy it. Feed that into our mass addition. This first one is going to be our stabilizing moment from the stand in Newton meters. And this one is going to be our destabilizing moment. In Newton meters. Right, now going back to our dispatched lists over here, we're going to choose list A from both of these, multiply them together, and list B from both of these and multiply them together. Because we'd already sorted out in this group over here whether or not the weight and the lever arm was on the left or the right hand side of our tipping point. So now what we've done is multiplied those together. We've got the results, and let's add a panel in so we can just check what's going on here, just to be absolutely sure. This is stabilizing, it's positive, yep. And this is very small, but it's positive. So let's just add in a multiplication, another way that we can do this. And there we go, we've got a negative number. And that's purely because of the way that I've set the code up. But it's fine, it still works. Right, group that together. And we want to feed in the last portions of stabilizing and destabilizing loads. So stabilizing moment from portions of the stand that are on the right side. Go in here. And you can see that the stand actually contributes most of the stabilizing moment, which we'd expect. And then destabilizing moment from the stand, we would expect a small number there, but again, small addition to the overall destabilizing moment. Okay, we're almost there. So I'm going to add these together. I can do that because we've differentiated between positive and negative. So I'm going to add. And then that is our total available moment. It's not necessarily the moment it's applied if the stand is very heavy, but it's the total available moment if the stand were to be at the tipping point. So let's add in a panel to see that figure, 259. Now label that total available moment in Newton meters. And then I'll just have an indicator here to tell me, or remind me what that actually means. So positive is stable. Let's expand it. There we are. Okay. And then let's put less than or smaller than. So if this is smaller than 0, we're going to set off a flag. So if it's unstable, in other words, we're going to have a boolean which will inform another part of our code, which you'll see soon. All right, so that's one group. And then we want to work out what the factor of safety is. So let's go to division. And we've got the sum of stabilizing moments divided by the sum of destabilizing moments, and that will give us a measure of how stable this is. So we can see that we've got 4.6 here. And So we can see that we have got a negative number in there. We can ignore that because we know that the negative is coming from the fact that we have applied a sign convention to destabilizing moments. What we're really interested in is the proportion of destabilizing moment to stabilizing moment. Let's round that so that we get a sensible figure rather than some crazy long decimal place. Round to decimal place. I reckon 2 is sufficient to really get a feel for the factor of safety. Let's feed that in, and yeah, just so that if we're going to display this in a minute, let's put in an expression x multiplied by -1 to get rid of the negative number. Add in a panel and label that factor of safety overturning. Okay, and there we are. We have our results. We've got the available moment. We know whether or not this is a stable solution by this Boolean we're outputting here, and we know the factor of safety. So let's group those together. And at the next tutorial, we will be looking at applying our genetic solver. So see you then.